okay.
I was just about to ask that.
All right. Sorry, I forgot to share. Can you see it now?
Yeah.
Okay. Sorry about that. For some reason, I thought I was sharing the screen. So yeah, let's do a secure shell. We'll go to Amazon Web Services, and it's a secure shell. And what it does is it gets me right in. And I've gone through an application layer and then a secure sockets layer. And I got a response back from my Ubuntu server, which is running on Amazon. So I've got a little cloud server running here. Here's another example. I'll just go to my Oracle cloud. And it's actually far more responsive for some reason. Actually, they give you a better forever free service than Amazon does. And so there's my Oracle cloud also up and running and zippy quick. So you can get to these things with relative ease. If you want to see how that works, check it out. So here we're just using SSH, and we have a key that we've shared and distributed, a private key, off to the Oracle cloud. And then I SSH in using the key, and I go into my little server, which is over in here. And that's an application layer that's using a secure socket layer, and gives me the ability to type into my shell. So yeah, OSI is alive and well, as far as I can tell. So that's that would be true. Let's see. Is it obsolete? No, it's false. It's not obsolete. So here's a question. Which layer provides a user interface?
Application layer?
Yep, application layer, sure. That's where we get things like the browser. So that sounds reasonable. And then here's a question. True or false? Routing is a service reserved for the transport layer. Where do we do the routing? What is routing? What is that? Any ideas? Better question. You know, how do I get from one little local area network to another? The answer is I go through a network appliance. What's that appliance called?
Routing.
What is the name of the appliance that allows me to go from one network layer, one local area network to another? In other words, I want to internetwork. Some people call it the internet, but internetworking is not necessarily involving the internet with a capital I. Internetworking means I have to be able to take packets and route them from one local area network to another. How can I do that? I need an appliance, a network appliance. Does anybody own any network appliances? Do you have networking where you live? People do use the network because they're on Zoom. So the answer has to be yes, because if you didn't have networking, you wouldn't be on Zoom. So presumably you have networking, and your computer probably plugs into a wire or a Wi-Fi signal that goes to a thing called a router, right? Routers are network appliances. You guys know about routers, right? That's a nice old router from the 80s, a router from the 80s. But you can see, here's a typical home office appliance, right? Somebody has an external connection to a local area network, and then there's local area networks internally, right? So you've got to route packets from one place to the other in order to get out the door to the other network. So you can see what routers look like. Oh my God, look at this one. That's like the first router, an interface message processor from the 60s. Wow. That must be in somebody's exhibit, right? Where is this thing anyway? UCLA? Oh, I gotta have this. The interface message processor, also known as the IMP. It's the IMP from Bolt, Bernack, and Newman. I wonder whatever happened to those guys. The IMP. So this was part of what was known as the ARPANET, Advanced Research Project Agency, which later became DARPA. So let's go back to the question. Routing is a service reserved for the transport layer. Is that true or false? We know what a router is now. Do we need it? Yeah, that's false, actually. And the reason why it's false is because you don't need the transport layer to do routing. The only thing you need for routing is IP, or Internet Protocol. So, for example, this here is an address which enables me to do routing of packets from one place to another. I can find my IP address by typing ifconfig, and somewhere in here I'll find my local area network address. And then I can also find my my router, ping 168.1.1. There's my router. And so at some level, one could make a compelling argument that you don't need TCP to do IP. You can do it with UDP IP, which is User Datagram Protocol, which is a connectionless mechanism for transmitting data from one place to another. Very similar to dropping a letter into a mailbox. The letter goes into the mailbox. We don't actually make a secure connection with the recipient. Instead, we're sending packets. So UDP IP is an alternative. And so transport layer is not responsible for routing. It relies upon the network layer. So the network layer does the routing and transport layer does the connections. Was there a question? So mapping a machine name to an IP address is the first step toward getting a connection to a machine. Does that sound right? Well, let's see. How do I get a connection to, let's see, ping to fairfield.edu. I think I can do that. Yep. Somebody mapped this domain name into an IP address. So when I go and get a connection to this, I'm really getting connections to there. And not to put too fine a point on it, if I bring up my my browser and type in that IP address, in principle, I should be able to gain access to a machine. Maybe I can do this without the S and avoid the warning. Oh, man. He really doesn't like it when I do that. Let's try this. Nope, he wants to put www in there. I think that must be a Firefox feature. Let's try a different browser. Nope, he wants to do that. That's his thing. He likes it.
The fuck? 1, 2.
See if I can get through. So I did, using the IP address. And so mapping a machine name to an IP address is the first step toward getting a connection to a machine. And that is true in general. That's true. You know, it's not, I guess it's not necessary if you know the IP address already, but then you did the mapping in your head. So you're basically playing the role of the domain name server. So yeah, getting the IP address from the machine name, that sounds like a good first step when you're doing a network mapping. You want to get through to something. It's like if I wanted to call you on the phone, first thing I want to do is look up your phone number. So that's a first step. So what's needed when communicating using sockets? What's a socket? What's that? Any ideas? Shall we use the Google? So a network socket is a TCP/IP protocol subroutine entity that allows me to make a connection between one machine and another using either a network name or an IP address. And you need a port number. So this is interesting. What's going on with the port numbers? Let's take a look. So here are our port numbers in my local Mac, right? And what these port numbers are doing is they're assigning services to different, I'll say, network entities. And sometimes the services are on TCP, and sometimes the services are UDP. So it's either UDP IP or TCP IP. And so, for example, if I wanted to go to my little Oracle cloud, I should be able to find port 80. And sure enough, port 80 is running TCP and UDP for my HTTP daemon. In fact, there's even a secure TCP. So it looks like I've got a service running on port 80. So when I connect to the service of HTTP, I'm connecting implicitly to port 80. But what about if I wanted to look at port 22? Well, port 22 is SSH. So when I SSH into my Oracle Cloud server, I'm using SSH protocol to the IP address on port 22. So sockets require a port because there's going to be an application listening for a connection on that port. And it's going to use the specification for that port and the protocol in order to be able to manage the connection. So that's kind of interesting because what that says to me is when I SSH into my Oracle server, I'm really coming in on port 22. But when I browse the web on my server, I'm really looking at port 80. So a socket server is listening for a connection, and presumably if you want to be a client of that connection, you need to open up a socket. And that socket is going to have both an IP address and a port number. And this is kind of important for people who want to do network programming. And network programming is kind of important if you want to think in terms of computer systems architecture. Because a lot of times what happens is computation is a service. And if you want to build a supercomputer with networks of workstations, you really have to be able to take advantage of that service by opening up sockets at some level or another through TCP/IP or UDP/IP, and then proceed to do remote job invocations. So getting back to the question, what's needed when communicating using sockets? Well, I need the port number. Got to have an IP address, which I can get probably from the name of the machine. And so all of the above, seems to me, you got to have it. Necessary but not sufficient. What do you think of that? Is that all right? Let's do another one. So here's a port. All right, something is listening for the port. It's occupying the port. It's a consumed resource. If a port is already being used, a server programmer need not find a free port for his or her service. Need not find a free port. What does that mean? What it means is if I have HTTPD, the Hypertext Transfer Protocol daemon, running in the background listening for port 80, and I want to use port 80 on my own little daemon, that creates a conflict. I've got to find a new port. So in other words, if I want two web servers to run on the same machine with the same IP address, assuming they're both sharing the same Ethernet card, then one is going to have maybe port 80, which is the standard port, and the other one could have port, make up a number, 8080 or 8086 or anything you like, as long as it's not the same port, because that creates a conflict. I can't just use ports, especially if they're part of the ensemble of services, and it causes a port conflict. So from the point of view of a programmer, I've got to find ports that are not in use, that I won't conflict with, and then I can proceed to write my own service. So if a port is already being used, a server programmer need not find a free port for his or her service. Is it true or false? Any ideas? Yeah, false. You got to find an unused port. Thank you. Let's do the next one. So let's look at this so-called server socket. Server socket. What is the role of a server socket? It says here, to provide communication endpoints that is used to listen for a connection request. So that sounds right. Forms a framework that is generally correct no matter what the protocol is. I don't know about that. Arrange the data packets that are out of order into sequential order. That sounds like a thing. Streams data in and out using connection-oriented protocol. I don't know. Is it possible for packets to arrive out of order? And the answer is sure. Why not? You can send them in any order you want. Is it a framework that is always correct no matter what the protocol is? That doesn't sound right. How about this? It streams data in and out using a connection-oriented protocol. Does it have to be connection-oriented? And the answer is no. You can use UDP. TCP is connection-oriented. So the only thing left is to provide a communication endpoint used for listening for a connection request. That's it. That's all it can do, is create a connection. Protocols you're going to have to handle yourself. If it's expecting an int, it's going to have to make sure you're sending an int, or else it's going to give you incorrect answers. So all it does is service a connection request, and that's it. So server sockets are actually entities inside of Java. And sockets are also entities in Java. And you can find the similar thing in C and C++ and C# and Python, and pick your language. You got to have some way to do network communications. Let's take a look at this other question here. DNS, what's that stand for? This is question 10. Domain name service is correct. That is correct. Thank you, John. So then a proxy is a service that manages connections between the intranet and the internet. Proxy. Proxy. Have we used proxies before? You guys probably have used them. Well, it certainly can be, but what is a proxy? What is that? Well, let's say you wanted to gain access to a list of all of the alumni from Fairfield University. You might go to the secretary and you could say, give me the list of all the alumni from Fairfield University. She serves as a proxy for that list. Send the alumni a message that we're looking to raise money. She serves as a proxy. So what you might like to do is use some sort of virtual private network and gain access to, let's say, Netflix from the United States, but pretend as though you are going through a proxy in the UK. So now when you're in the UK, maybe you can sit there and watch British television because, well, maybe because you like it. And you can't get access to the British television in this country because I guess Netflix doesn't let you watch it when you're in this country. It might be like you want to watch the latest Doctor Who or something like this. So you have to go in through the UK, and once you're in the UK, Netflix will let you watch Doctor Who all day long. So you go through a virtual private network that serves as a proxy and manages the connection between your local area network, your intranet, and the internet. So that's a proxy. Let's take a look at some other interesting networking ideas here. So which of the following are steps involved in distributed computation on the server? Read an instance of a computable object. That sounds like something good. I get it down with that. That's good. A computable object. Perform the computation. All right, that sounds all right. Process the answer and send back the answer. Which of these are involved in distributed computation on the server? So if you're on the server, what would you do? Would you send back the answer on the computation server? I guess you'd have to. Do you want to perform the computation on the computation server? I'd say, yeah, why not? That's what it's for. Would you want to read the instance of the computable object? Sure, because that instance is the thing you're going to do the computation with. And what do you do with the answer? Well, you don't know, right? That's the separation. That substrate says we invoke the computation on the computation server. It does the computation and sends back the answer. We have to process the answer. That client processes the answer, not the server. So when you're doing a distributed computing process, you'll read an instance of the computable object on the compute server, perform the computation on the compute server, and send back the answer from the compute server. Then somebody, the client, is going to have to process that answer. So if you said to the server, please process and render frame number 30 of my movie, it'll send back frame 30, but it's up to you to put it in order and actually play the movie. So that's a processing of the answer. That's done on the client, not the server. Does that sort of make sense to people? Am I going too fast here? You're all very quiet. Looks like we have a nice full class. So, and this is being recorded in case you need to refer back to it later. So then let's take a look at some of this other stuff here. A client must be multi-threaded so it will not block during computations. Must be. Must be. Do you think it must be? What does it mean to be multi-threaded? You guys have heard me ramble on about multi-threading for some time now. In case you have some questions about that, you can always refer to the Google, I suppose. Multi-threaded wiki. What is multi-threaded? So here is a process which contains many threads. They all share memory, which is both good and bad. It's good because it leads to a low overhead context switch. It's bad because, well, they're sharing memory, so they can step on each other's toes. I was just looking at this wiki page. Super threading. I don't know about that. Temporal threading. Sometimes I think this is marketing. So, a client must be multi-threaded so it will not block during computation. So, if you have a multi-threaded client, it will not block during computations. That's true. But must it be that way? And suppose I said to you, let's do an example. A equals B plus C. The left-hand side will not be assigned until the right-hand side is computed. That blocks the primary thread of execution, and rightfully so. I can't assign the equals until I know the result of A plus B. I can compute B in a separate thread from computing C, and then I could compute plus altogether or gradually, but until that whole thing is computed, I can't know A. So blocking the primary thread of execution during the computation is an appropriate thing. And I don't have to put it into a separate thread, especially if I need it in order to continue computations. So I would regard that as false. Question 13 is false. So which of these are steps involved in distributed computation on the client? On the client. So before we did computation on the server, what does the client do? If there's a computable instance, a computable object, does it have to read it? No, it already has it. But it does have to send it, and it's got to get it back an instance of the answer. So you send the computable object off to the compute server. It does the computation, sends back the answer. Now you have to process the answer, and you have to get back an instance of the answer. So I say 2, 3, and 4 are correct. How am I doing here so far, folks? Am I going too fast? So if you're trying to follow along in the reading, what you're trying to do is if you can get to the Java for Programmers book, page 479, that's going to have that for you. And I think we've got a copy of that book available. And it was, I think we put it up as on reserve in the library, although I don't know if people are able to get to the library nowadays. There's also electronic versions of it available on Amazon. And I think there might even be something of a chapter or so on the in the Blackboard. And we can check that if you like. So that's the book. So that's going to be our Patterson and Hennessy book. Yeah, I'm not seeing it here. Let's just take a quick look. Well, we can fix that. If there was ever a question about something like this, like what's an SMTP server? I suppose one way you could do is to Google it. And there it is, simple mail transfer protocol. And look at this, it says it's on port 25. So transmission control protocol, TCP, on port 25. So what does this mean to me? Probably means that if I go to Etsy and look at services and look at for port 25, there it is, simple mail transfer protocol. So there's a great example of a layer on top of TCP IP, because look at this, he's using both TCP and UDP, and then he uses another protocol on top of it. He has to start a session. He has to manage logins. He has to keep it secure. So at some level, one could make a compelling argument. There's a great example of an application layer, email, using a presentation layer and a session layer in SMTP, simple mail transfer protocol. And it's been around for a while, right? Since 1982. Email is not new. And oddly enough, it wasn't invented by Al Gore. Gee, I thought everything was invented by Al Gore. I thought he invented global warming. Didn't he do that? So yeah, port 25. So simple mail transfer protocol. I think we saw that already because it was on the net. And then here's a little Java program. You guys know Java, right? It says here, consider the following code and write a Java program that can obtain a MAC address of the local machine. You may return the address as a string. What does this say in here? This is scrolling off the screen for me. That's question 17. Let's see if it's in my printout. Yeah, it's scrolled off the page on my printout as well. Use OS utils to determine which command to run. ifconfig A for Unix. What does this do? ifconfig A. Let's take a look. I don't know, but I think that'll work here. ifconfig -A. Yep. Let's pipe it into more. And it seems to work. Gives us all kinds of interesting and wonderful information. If I was on Windows, it would be ipconfig/all. And if I'm on Unix, ifconfig/A. ifconfig, oh, it's -A. My bad. Oh, yep, it works. So here's the IP address for my my little EC2 server. That's a micro instance running on the Amazon Web Services platform. Micro instance. So here's something called the Stream Gobbler. Oh boy, that sounds good. That sounds like a Spider-Man menace or something. So extends thread, and it uses a thing called an input stream and another thing called an output stream. What's a stream? What's a stream? I've heard of these things. Some people use the term streaming. Have you ever heard of streaming? I think Netflix does streaming. Don't they stream something? What is streaming? Does anybody have any idea about that? Can we Google it? Can we Google streaming? Somebody should know what this is. Streaming, there's streaming media systems, streaming television. What could streaming be? What is a stream? A sequence of data elements. There you go. For me, a practical application is an unformatted sequence of bytes. That's it. So a bunch of bytes, binary data, don't know what the format is, don't know what the data is, don't know anything about it. But basically, it's just one byte after another. And if you think about it, it's like a file of unknown type with no end. A file with no end. Because if you have streaming radio services, right, the radio doesn't like have an end of file marker. It just keeps giving you data. So an input stream is a way in which you can read bytes. Maybe figure out what the format is later. An output stream is a way in which you can write bytes. And so the stream gobbler has input of a given type. And then it has this thing here, which is a constructor, which takes the input stream and the input type, which apparently is a string, and then this other element, which is null. So it calls an output stream redirect and supplies null in there. Then here comes the run method. And so the run method is interesting to us because this is a thread. And threads are going to give us a kind of inversion of control framework where they call back to the thread using a scheduler and it invokes the run method. That's how threads run. So when you start this thread, it will become ready to run, and then the scheduler will proceed to invoke the run method inside the thread. And what it does is it makes a print writer over in here from the output stream. And then he makes an input stream reader from the input stream. Then he proceeds to read from the input stream using a buffered reader one line at a time. So he does a br.read line, brings in the line, and then takes that line and prints it to this output stream. And so what is it doing? It's copying the input stream to the output stream and treating it as text. And when he's done, he does a flush, because there may be a cache where everything doesn't get written out all the time. And that is a straight copy. And here's how you invoke the class with a main. And looks to me like he's going to run ipconfig all in the runtime of the local virtual machine. He's going to execute this program in there and give us a thing called a process. We'll take the process and pass it into the stream gobbler and print out the output of that process if there's an error. And otherwise, it's going to give us some sort of result, presumably from invoking ipconfig/all. And then when we hit start, it becomes ready to run. It's two different gobblers, apparently. A stream gobbler for processing error and a stream gobbler for processing the output stream from the process. And this says to the process, wait for it to finish. Gives us an exit value. If there's an error, we'll be able to tell. So that sounds like a thing. What does it say we have to do with this? Consider the following code and write a Java program that can obtain a MAC address of the local machine. You may return the address as a string. So this looks like it will do that. How would we run this program? I suppose I could, in theory, type let's see what it looks like. Stream gobbler. Well, does it have a yeah, the public class is called test exec. I guess it'll compile. I don't know. Yes. I didn't use the command properly. Oh, the usage is not ipconfig? What was I trying to run here? Emacs test exec. Am I trying to run ipconfig or ifconfig? Somewhere in here, there's a process. It says ipconfig/all. On a Unix system, it's ifconfig-a. On a Windows system, it's ipconfig/all. Let's see if that's right. Yeah. So we'll recompile. And then let's see if we can, yeah, that works. So here comes the stream gobbler giving us the output from our invocation. Isn't that cool?
Professor,
Yes.
Could you go over that one more time a little bit slower so we could understand how to do it on our own terminal?
Sure, sure. So what I did was I took this code, which is got a public class in it called testexec. And because it was a public class, I knew the name of the file should be testexec.java. And then I took this whole thing and I copied it right up to the import. Oops, I went a little far here. I just want to go, I don't want to include the question. I just want the code. So I went all the way down to the bottom of the code, hit copy. And then I went into testexec.java and I pasted it in. So here's my pasting. And let's say the formatting is pretty lousy on this. But I think that might be a Blackboard thing, because if you had a normal IDE, it would format this properly. But I'm just using whatever Blackboard gives me. And there's the command. Now this command is going to have to be able to run from the command line. And it will if you're on a Mac. If you're on a Windows system, it's got to be ipig_all, which is how it started. But because I was on a Mac, or a Unix system for that matter, I had to use ifconfig-a. The ipconfig/all, yeah, he didn't like that.
What is the Emacs testexec.java? Like, how did you get into where you pasted the code?
Oh, I just typed in Emacs, my favorite editor. And then you could type in Notepad if you like. I don't know what operating system are you in?
A Mac?
It's a Mac. Okay, so if you open up a terminal window, do you know how to open up a terminal window?
Yeah.
Yeah. So then when you open up a terminal window, if you have Emacs installed, and if you don't, you can use something like brew install Emacs. I'm not going to run that here, but right now it's going to go through a process and it takes forever and whatever. I'm not doing that now. Stop it. Stop it. So basically it's you need to install Emacs if you don't have it already, but you need some sort of an editor. I'm using Emacs because I didn't feel like using IntelliJ. If I wanted to use a proper IDE, I could start IntelliJ and I could paste it into IntelliJ if that's the sort of thing you like to do. Normally, I don't do development in Emacs. Normally, I do development in IntelliJ. But once you get involved with, running IntelliJ and doing large projects and all this other stuff, it tends to have its own overhead. But if you did it in IntelliJ and you said new Java class, you could give it the name testexec, and then presumably paste in the code. That is not the code. And now, if I said code, reformat the code, it doesn't make it nice? That's terrible. Well, anyway, it does what it does, okay? It does what it does. So I'm on IntelliJ now, and I'm going to try and run ifconfig-a. And then I think maybe it'll work. Yeah, and there you go. So you can actually do it in an IDE if you like that better. It wasn't all that much slower. Just had to start the start the IDE up. What do you think of that? So now you've got the input stream gobbler. It's a thread. And it's going to invoke the run method over in here. And you know the run method is running because you can type S out, Control J, enter, Mickey Mouse is my hero. And then presumably when you run it, somewhere in here, it'll type that out. And there it is, it's typing it. So this is running, and it's being invoked by the thread scheduler. For some reason, it printed it twice. Now that I do not quite know why it would do that. It's a little bit weird. Oh, maybe because I made 2 instances of the stream gobbler. And this is the first thing the stream gobbler does, is print out Mickey Mouse is my hero. So that's why. I was going, why does it print it twice? And the answer is because you made 2 instances. And you started them both. So it printed it twice, which is completely sensible. Just what it was supposed to. It's doing exactly what it's been told to do. So that's fine. What do you think of that? Does it make sense? So you got a little Java lesson in there. Not too much Java lesson, but a little lesson. Maybe it makes sense to just stay with it for just a little bit. We'll put in a new class. We'll call this the thread test. Okay, thread test. And what we'll do is we'll make this extends thread, and oh, even better. I've got an even better way to do it. Implements runnable. That's the best. Implements runnable. So if it implements runnable and it's not abstract, then it must have a run method. So we implement the methods, and it's run, and it's required. And now what we'll do is we'll say S out, quote, hello world. Okay. And now to get that to run, we'll have a main method, and we'll make a new instance of the thread test. And what do you think will happen if we run it? The answer is not much. Not much. Why not? Well, because we didn't start it, right? So tt.start makes it ready to run. Sorry, you have to make a new thread. Thread t equals new thread. Put in the runnable element, then call t.start, and there you go. You can see I'm a little bit rusty, but that's okay. I'm getting it. And now it says hello world. So we've run our first thread, which is great. Happy day. And now I'd like to know, how many threads we have. So what we'll do is we'll put in a static integer for the thread count. We'll call it TC and set it equal to 0. And then every time we make a new thread, we'll increment the thread count. And then when we, print, we'll say this is thread number, colon, and then plus thread count. So we'll know what thread is running. And then, maybe we'll make a little for loop, shall we? For integer I equals 0 while I is less than 1,000. Let's make 1,000 threads, I plus plus. And we'll just put that into a little loop. And we'll just keep making the new thread test instances and running them. And each time we run them, we'll have a different thread number. And that should work in theory, I hope. And there we go, 1,000 threads, no problem. Now you couldn't do 1,000 jobs under any operating system without substantial pain, but they all share resources. They're all sharing CPU time. They're all sharing memory. And if you wanted to, the run method could invoke a sleep function that thread.sleep and let it sleep for n milliseconds, where n is math.random, some random number times 10,000. And that'll give me a long integer for my sleep time, st, and we'll just cast it to long. And that should give us, what's his problem? You want to cast it to int? Oh, it says long int. No. It can't be a long int. It's either a long or it's an int. And now we'll sleep by sleep time seconds, and that needs to be caught into an exception. So we put it into a try catch block. And now I think maybe they'll all be sleeping. All the threads will wake up and at random times, and eventually we'll, that might be too much sleeping. For 10 seconds later, we should have everything running. So we can see they're instantiated at different times. Eventually, there were 1,000 threads total. When they're created, they should probably capture their thread number. So that'll be a volatile integer thread number, which will be equal to the thread capture, the thread count at the time. And then when we print, we'll know the total number of threads. That's fine. It'll be 1,000. But we'll want to actually know the thread number, because each thread will have its own number. And that's because this one's, volatile. The other one is static. So the total number of threads won't change, but the thread number keeps changing. And you can see they're all waking up at different times, and that's 1,000 threads. And so now if we wanted to, we could, I don't know, up our game a little bit, go to 5,000 threads. What could possibly go wrong? Could run out of memory, I guess. And he seems to be able to handle it, and the threads are waking up and running asynchronously with respect to one another. So there's multi-threading for you. 5,000 threads, no waiting. And not a problem. Not a problem. And each thread could handle its own server socket, which means if my web server goes live with threads, I should be able to handle all the visiting clients, as long as I don't do too much computation on the server. So that's the multi-threading lesson right there, and it's all done with a for loop. For loop, something that's runnable, making new instances of threads, and then starting the threads. And the threads will run. And as they run, they may have to, I don't know, sleep a random amount of time. And then when they wake up, they'll print out their thread number and then die. Once the threads die, they're removed from the heap, and the memory is returned to the virtual machine. Threading. How exciting. We got to threading. That's actually good. That was educational, wasn't it? sort of, educational. So here's an example of getting the date and time from NIST. And so NIST is the National Institute of Standards. And so they provide us with a host. And now we're going to use an internet socket. Here's a new socket. So that's a client. NIST is providing us with the computation server. And what we're going to do is we're going to make up a new internet socket and go to this host name, which will have to be mapped to an IP address. I hope it's still good. Let's just sort of go into our, they're still there. That's good. That's good. Yeah, I was worried. So yeah, if you wanted to go into this time server and go into port 13, in theory, you just type 13 and telnet, if you have telnet. I don't know if I've installed telnet here. Yeah, I did. And so when you telnet in to port 13, you get the time and day service from the National Institute of Health, National Institute of Standards and Technology. And then that is being run by a cesium atomic clock. So this is like a super precise means of getting the time, except that there's latency in the network. And so what they do is they compensate for that, or you can compensate for it when you get the ping time. So this program opens up a socket to NIST and gives you a timeout of 1,000. Whoops, it says Blackboard help. Stop it. Stop it. No. Blackboard takes over. So then we go and get our input stream. That's the unformatted sequence of bytes. We make our input stream reader from the time stream. We go and get our buffered reader, right? This is a nice example of distributed computation. Buffered reader then says read a line and then print out the line. And so we're going off to NIST, and then we take whatever it gives us back and we make a new instance of a calendar and we print the date and time. And this is a matter of parsing the calendar information from NIST, which is a whole other problem, parsing NIST time. And so if you want to, you can copy this and you get a nice example of doing the date and time from a server, which is kind of cool. Isn't that cool? Here's an example of getting the date and time from NIST. Very cool, very cool. What do you think of that? Is that too much Java by half? Consider the following code and write a Java program that can obtain the MAC address of the local machine. You may return the address as a string. So where is the MAC address? That's the media access control layer address. ifconfig/a. Where is the MAC address? ipconfig. -a. ifconfig. Ay. I go back and forth between different operating systems and it gets me all messed up. So this, right there, that's your MAC address. That is the hardware address unique to the Ethernet device. And so that is how you do a local area networking as opposed to internetworking, or this allows me to go from one Ethernet card to another Ethernet card, or from one Ethernet card to the router. The router is going to have its own MAC address. And so that is the MAC address we're looking for, such as it is. So consider the following code and write a Java program that can obtain a MAC address of the local machine. You may return the address as a string. Let's see. Use OS-utils to determine which command to run. OS-utils. Let's take a look for that. That's actually, this is like an interesting project because this is not a particularly difficult project because it doesn't have a lot to it, but you have to sort of find stuff. Let's see now. Find in path, OS-utils. Here it is. So if it's a Mac, is get Mac address in here? Get OS name. So this is how I run an exec command. But in fact, we just saw how to do that from the homework. And what else do I need to know? Here's test ifconfig. You don't really need it because you got everything you needed from Blackboard. Right? Because Blackboard used the stream gobbler to invoke the command ifconfig or ipconfig, depending upon your operating system. If I had Windows, I'd show you ipconfig, but this is a Mac, so I can't really show you. Then it does the process and proceeds to do the printout. So all you have to do is isolate the part that shows the MAC address. Presumably, when we ran the program, we ran Java test exec, and somewhere in here, you can see a MAC address. And maybe more than one being shown. You know what you do is you pipe it into more. That's the way to go. So there, where it says ether, that's your MAC address. So if you said rep on ether, you can see all the MAC addresses being put out. So there is more than one, and you can isolate them. And the question of why there's more than one, it's probably because I've got a MAC address for my Wi-Fi. If I turn my Wi-Fi off, that ought to remove one of the MAC addresses. So it got a little bit shorter. There may be other ways I'm getting a MAC address here. I wonder if Bluetooth is going to do that. Probably not, but we'll turn that off too and see if, no, it doesn't get any shorter. I think there's probably one for IP version 6, IP version 4, and I'm not sure what else there is. Oh, it says it's got a loopback running multicast. I don't know why he's doing all that. Oh. I wonder if that's Zoom related. I've got all this broadcast stuff going on. I bet you Zoom sits around and creates all this extra stuff. I'm not convinced that I normally run all of these point-to-point multicast things. That sounds like a Zoom thing to me, I'm thinking. All right, so that's what I have the time for today. Give this a try. You know, try and cut and paste some of this code in. See if you can run it. I think it's kind of educational, even if you haven't had a good networking course. Because if you want to do, you know, distributed computing and parallel computing, you got to do a little programming, I think. And having done a little bit of programming, I think you'll have a little bit more confidence in this kind of programming in the future. At least you'll have tried a small program, and maybe there'll be some learning going on with that. So have a good day, everybody. Stay safe, and thank you for your attention.
Thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.
Thank you.
Professor,
Yes.
so for question, the one that you were just going over, 17, all you're
Yes.
looking for us to do is copy and paste that code into like an IDE and attach a file for question 17 that has the output of it. That's all you're looking for us to do.
Yeah, I think that's right. You're gonna somewhere in that printout, like I showed you, you're gonna find the MAC address. And the way I did it was I just used grep. So if you said something like bang 32 grep ether, you can see the IP address. The MAC address is coming out where it says ether.
So it's okay if we just copy and paste the entire output of it into a Word doc to submit?
Well, you might like to identify, it's asking for the MAC address. So you might like to identify the MAC address, and that's it. This is the
Okay,
MAC address.
and that's what's right after ether?
Yeah.
Okay.
Yeah, I just used grep because it was convenient under Unix. I don't know if there is a similar thing in Windows. Are you using Windows?
I'm using Mac.
Oh, okay. So you should be able to find the grep.
So
Grep is built
but
in.
the output has multiple ethers. Which one exactly is the correct?
I think they're all correct. They must have started them. I really don't understand why there's so many things going on. I'm going to quit out of Zoom after we're done, and I'm going to check this again to see if Zoom hasn't created a whole bunch of multicast stuff. I haven't really studied what Zoom does to my computer, but it makes the fan go fast and it makes it really hot and bothered. So I have a feeling Zoom is like doing a lot.
Okay.
Yeah, I don't think you're going to have the same number of Ethernet connections that I have.
Okay.
So, but you can list them all.
Okay.
Okay.
Thank you.
Thanks a bunch. Bye-bye.
Bye.